Hello and welcome to this fourth session on atomic structure. So at the end of last time we had this exercise on helium and the shielding that one electron does on the other electron. We saw last time that we couldn't just approximate it to being nothing or approximate the shielding to being perfect. It's going to be some intermediate amount of shielding, and we're going to try and quantify that now with this exercise. And that's to say, to find the shielding parameter S. And so this is the S that we subtract from the actual nuclear charge Z to give us the effective nuclear charge, ZF, that the electron experiences. And so what we're going to do is we're going to take the actual total electronic energy, minus 2.9 Hartrees, which we found from the experimental first ionization energy plus second ionization energy of helium. And so what we're going to do is we're going to equate this then to the energy expression, which involves this minus a half Z effective squared divided by N squared. And so by substituting for Z effective, Z minus S, ultimately we're going to solve for S. So you may have worked this out at the end of last time, or you might like to pause the video here and have a think about it, and I'll give you the method in just a moment. So now on to the answer to this helium shielding exercise. Well, that total observed electronic energy of helium, minus 2.9 Hartrees, we divide this by 2 to get the energy of each electron. Obviously these are two 1s electrons, so there's no reason why one electron should be different energy to another. So we just divide the total energy in 2 to get the individual electron energies as 1.45 Hartrees minus 1.45. And so then now we apply this equation, which is a one electron equation essentially. And so we substitute in minus 1.45 for E. N there, this is the shell number, which is just 1, obviously, for helium. And then we solve for Z effective. And so the effective nuclear charge comes out there as 1.7. So since the actual nuclear charge was 2, that means that our S parameter in this case must have been 0.3. And this is an established idea in the so-called Slater's rules. So of course Slater would have done his calculation himself back in the 1920s, and we use this value 0.3 for the shielding parameter for a 1s electron on another 1s electron. We do this all the time. And in fact, Slater did a great deal of work using lots and lots of observed energies, ionization energies, for lots of different atoms. And he looked to work out these energies in terms of this simple model and fitted as best he could all his theoretical expressions for the energies to the observed energies. And as a result of all this work, he hit upon a series of rules for determining approximately what these shielding parameters ought to be. And so it's by no means perfect, it's a fairly rough and ready model, but by averaging over lots of atoms, he's found some fairly decent rules which work fairly well most of the time. And these are the so-called Slater's rules. But before we get into the Slater's rules, I just wanted to give a health warning about effective nuclear charge, ZF. And I think this can be somewhat misunderstood and misused as a term, so I was just going to go through some of these ideas now. And so really it's all about how the nuclear charge is, as it were, moderated by other electrons in the atom when you're looking at it from the point of view of one electron in particular. But I think very often, especially at AS level, when we're looking at trends across a period, for example, I think quite often effective nuclear charge is used when what we really mean is nuclear attraction. So I just wanted to flag this up now. And so if you're talking about the attraction to the nucleus that an electron experiences, then really the energy, that attractive energy, is the thing you're really referring to. But that energy is going to be proportional to the effective nuclear charge divided by the distance from the nucleus r. And so we saw when we saw the total electron energy as kinetic energy plus potential energy. You remember this came to half of the magnitude of the potential energy, and this involved the nuclear charge on the numerator and the distance of the electron from the nucleus on the denominator. And so we need to remember that the distance of the electron from the nucleus is a separate factor we need to consider. It's not something we can just lump in with the effective nuclear charge. And so I think we often see an error when asked about the ionisation energy, for example, decreasing down group 1. I think it's quite a common response to say that the effective nuclear charge decreases down the group. But actually that's not the case. What's happening down the group is that the outer electron is in a more distant shell from the nucleus. And it's that extra distance from the nucleus, that's the reason that the ionisation energy goes down. It's the R, the distance from the nucleus factor. Curiously, when you go from sodium to potassium, the outer electron actually experiences the same effective nuclear charge. And this is because when you go from sodium down to potassium, of course you gain another 8 protons in the nucleus, and you gain another 8 electrons, and those 8 electrons will actually be like a core. It'll be like a new second shell. There's a core of 8 electrons near the nucleus, and that effectively shields the valence electron. So it kind of cancels out the other 8 protons that you put in the nucleus. And since the extra protons in the nucleus and the shielding from the extra electrons cancel out, you actually have the same effective nuclear charge. So really it's the distance from the nucleus on account of the highest shell. That's the real reason that the ionisation energy decreases down the alkali metal group. Now onto Slater's rules themselves, and they're all summarised here on this slide. And just to say that when we looked at the helium case, there was only one electron doing shielding in the helium case, because there were just 2 electrons altogether. But these rules are set up for us to deal with more complicated atoms with many electrons. And so what we need to do is we need to sum over all the shielding contributions from all the other electrons. And so this is why we introduce into here this lowercase sigma. So the lowercase sigma will be the shielding contribution from one of the other electrons in the atom. And what we do is we sum over all the other electrons in the atom to give us the overall shielding effect experienced by our electron of interest, and that's the capital S shielding parameter. And so the way Slater went about it, as you can see here from the first rule, is the S and P subshells. He considered them together because they are very similar in energy, the S and P subshells within a given shell. So he grouped them together, but the other types of subshell were considered separately. And so he considered the electrons within these groupings. And so in our rule number 2 there, sigma equals 0 for electrons in higher groupings. So this is essentially saying that if you're looking at the shielding that an electron experiences, then an electron in a shell outside it isn't going to shield it at all. So in other words, if you're a 2s electron, then a 3s electron isn't going to shield you from the nucleus at all. So that's sigma equals 0. That's no shielding contribution from an electron in a higher grouping. However, if the electron is in the same grouping, then you get this partial shielding, not very efficient shielding. Actually, you could say 35% efficient, because we've got this sigma equals 0.35. And this is what we refer to when we talk about ionisation energy generally increasing from left to right across a period, because you're adding more valence electrons to the atom and they're not shielding very effectively from the nucleus. So they're only 35% efficient. But in the specific case of the 1s orbital, we use 0.3, so that's the exact value we calculated in our exercise with helium. Now, when it comes to the shielding from an electron inside in an inner shell, this is obviously much more effective. So for S and P electrons, so for example, if you're a 2s electron and you're being shielded by a 1s electron, then that will be an 85% efficient shielding. So sigma equals 0.85 will be the contribution from each electron in an inner shell. And if you are 2 shells inside, it becomes 100% efficient. So a 3s electron would be shielded at 100% by a 1s electron. You'd have sigma equal to 1. And if you're talking about D and F electrons, actually all the other electrons in lower groupings are 100% efficient. Sigma equals 1. And so what we do is we collect together all the shielding contributions from the other electrons. And this is this capital sigma there, summing over all of the little sigmas, the contributions from all the other electrons. And that gives us our overall shielding parameter, which we subtract from Z, the nuclear charge, to give us our effective nuclear charge, ZF. And the final point, it just relates to the fact that for higher shells, we also tweak the N value. But we're not really going to look too much at higher shells. It's a bit too laborious, really. So there we are. They're the Slater's rules. Probably worth taking a screenshot of this or something. They're very worthwhile rules. We can do a lot with them. Now, some general comments about ionisation energy. So, of course, we looked at ionisation in the supernova question, and that was in the context of hydrogen or a hydrogenic atom. That's to say an atom with only one electron. And so ionisation in this case, it's trivial really. There's just the one electron that you're taking out of the atom. So just minus the electron's energy will be equal to the ionisation energy. But actually when you've got a multi-electron atom, the ionisation process is actually quite a bit more subtle when it comes to this kind of calculation. Because really what you need to do, and this is the point I'm really emphasising in the highlighted part on this slide, what you really need to do is you need to look at the total electronic energy of the atom to begin with, the total electronic energy of the atom after the ionisation has happened, and then you need to look at the difference between these two totals, and that is the ionisation energy. And of course it's very easy just to assume that it's just the energy of the electron that comes off that you take to be the ionisation energy, but it's actually all the shielding business that complicates the matter. So in a multi-electron atom, if you remove one electron, not only is there the energy required to lift that electron up to the, if you like, E equals 0 ionisation limit, but having removed that electron, it means all the other electrons in that shell and in outer shells, they will all experience a different amount of shielding, because obviously the shielding contribution that was there before from that electron has gone. And because they experience different shielding, that means they experience a different effective nuclear charge, and that means they're at a different energy. So actually these electrons all affect each other in their energies, and that's why we need to take all the electrons into account and then look at the difference between these totals when we work out the ionisation energy. So now we're going to work on a problem here, and so we're going to try and work out nitrogen using the Slater's rules. We'll work out a value for the ionisation energy, and of course there'll be an experimentally determined ionisation energy as well, which is 1402 kilojoules per mole according to my data book. We can easily convert this to atomic units and then do the calculation in atomic units, which will be much more straightforward for us. So as I said, we need the total energy before and the total energy after. So yeah, quite a laborious process, taking all the electrons into account. But when you think about it, you'll realise that actually there are some shortcuts. There are some energies that should cancel out. So you might like to give a bit of thought. In the case of the nitrogen atom, which electrons' energies would cancel out in that calculation? Right, so let's look in a little bit more detail at what we need to do to get this ionisation energy. We're going to have to look at the shielding involved. And so that last question, which was about energies cancelling out, this is about the 1s electrons. Because of course when you ionise a nitrogen atom, it's the minimum amount of energy to ionise the atom, so it's a 2p electron that we're removing. That's one of the higher energy electrons. But of course the 1s2 electrons, not only are they not directly changed, in other words they're not ionised in the process, but actually even the valence shell, which is affected by the ionisation process, isn't going to change the 1s electron energies, because remember the Slater's rule said that sigma equals 0 for electrons in higher shells. So the 2s and 2p electrons have no shielding contribution to the 1s electrons. So those 1s electrons' energies are going to be completely unaffected by the ionisation process. And so we can just forget about them, because if you work out those energies, they're going to cancel out anyway. So we can forget about the 1s electrons, but actually the 2s and 2p, we are going to have to look at those carefully, because the electron that's being ionised is from this shell, and so it's going to affect the shielding. And so now we just apply Slater's rules. So those 2s and 2p electrons, first of all we can say that they're going to be shielded by the 1s electrons beneath them. And so using our Slater's rules about s and p electrons being shielded by the shell underneath, each electron contributes sigma 0.85. And so they've got 2 electrons doing that shielding in 1s2. So we multiply 0.85 by 2, and that gives the amount of shielding from the 1s2 electrons. And then next we can think about the valence electrons shielding each other. But of course we've got 2 different cases to consider. We've got the nitrogen atom, and then we've got the final state, the N+ ion. So if we look at the atom first, there are 5 valence electrons in the second shell. So as far as any one of those electrons is concerned, it's experiencing a bit of shielding from the other 4. And each of those other 4 will contribute sigma equals 0.35 from the Slater's rules, this fairly inefficient shielding. Whereas in the N+ ion, of course, there's only 4 electrons in the valence shell left over after the ionisation process. So for any one of those 4 electrons, they're getting shielding now from just 3 others. And so therefore, each of those valence electrons has sigma equals 3 times 0.35 shielding from the other valence electrons. And so what we can do is we can take all of these sigmas into account. We can be adding them up and working out the total shielding experienced by the valence electrons. So in the atom, we've got 2 lots of 0.85 from the innermost shell, and we've got 4 lots of 0.35 from the valence electrons, and I think that should all add up to S equals 3.1. But when you look at the N+ ion, it's much the same, except one of the valence electrons is missing, and so the total amount of shielding there has gone down by 0.35. So that's why we have this S equals 2.75 for the valence electrons in the N+ ion. So I think having done this preliminary work now on all the different shielding contributions, hopefully now we've kind of prepared the ground to calculate the ionisation energy. So what you might do at this point is stop the video, look at the numbers, think about the equation that you need to use, see if you can work out the ionisation energy, and then in a few seconds I'll show you on the next slide. Right, now finding the ionisation energy of nitrogen. Okay, now one thing I'd just like to emphasise now and to recap is that this equation we've been using, E equals -1/2 Z effective squared over N squared, we're basically making use of the equation that we'd established for hydrogen. So this is essentially a 1 electron equation like we would use for the hydrogen problem. Except what we're doing is we're just moderating the Z, the atomic charge, to take into account the shielding effect of the other electrons. So even though it's a multi-electron atom, we're still treating it in a way as if it's a 1 electron atom. And so what we're doing is we're taking 1 electron at a time. For each electron, looking at how all the other electrons contribute shielding towards it, take that into account by reducing the nuclear charge by the S shielding factor to make the effective nuclear charge, working out the energy of that 1 electron. And then we'll simply go over that process again and again for every other electron in the atom, and then sum it up to the total. So we're kind of breaking our multi-electron atom down into lots of little 1 electron problems, where all the other electrons, apart from the one that's being considered, are just kind of lumped together in a way that reduces the charge on the nucleus. So we've worked out all the shielding parameters that are experienced by all the different electrons. Now we can start substituting them into the equation. So Z obviously is 7, it's the atomic number, minus S, depending on which electron we're looking at, divided by N squared. And in fact, we're going to be just looking at the valence electrons, and so N is always going to be 2. So remember we were saying we don't actually need to worry about the energies of the 1s electrons, because actually they're going to cancel anyway when we look at the difference between the atom and the ion. So looking at some of these specific cases then, so when we look at the valence electrons on the nitrogen atom, we substitute in S equals 3.1, the shielding parameter, put that into the equation, and it gives us the energy then for one of those 5 valence electrons comes out as minus 1.901 Hartree. Then we do the same for the valence electrons in the N plus ion. So the shielding parameter was a bit less for this one, 2.75. Put those numbers in, and so we find each energy, the energy of each valence electron in the N plus ion is minus 2.258 Hartrees. And so when we come to find the ionisation energy, we're now having to sum over all these 1 electron energies to establish the total energy of these systems. So first of all, in the first bracket there, we've got 4 times minus 2.258 Hartree. So because there's 4 electrons we're looking at here, this must be the N plus ion, the 4 valence electrons. And we're subtracting from that the total valence electron energy of the nitrogen atom, which is why we've got the 5 in there, 5 valence electrons, 5 multiplied by the minus 1.901 number. So if you think about it, the N plus ion is going to be at higher energy than the N atom. And it's because we've had to put energy into the system to ionize it. Of course, ionization energies are always endothermic. And actually the number is going to look smaller, but it's a smaller negative number. So, a smaller negative number is larger ultimately than a bigger number that's negative. So we subtract the nitrogen atom energy from the N plus ion energy, and then we get this value 0.475 Hartree. And then what we can do is compare this with the true value, the experimentally observed ionisation energy of 1402 kilojoules per mole. So we divide that by the conversion factor, and that comes out as 0.534 Hartree. So comparing those numbers, we can see it's not a brilliant agreement, but it's not absolutely miles off either. It's sort of just about acceptable. It agrees to one significant figure. So that's something. It's better than the approximations we'd made before, where we assumed there was either no shielding or perfect shielding. And it's curious because you can do this I've done this for lots of other atoms actually. You can get a spreadsheet together to kind of automate the process. And I find that in some atoms you get better agreement, some atoms you get worse agreement. And so I chose nitrogen as its kind of average of the range or something like that. So it just goes to show that this approach with Slater's rules, which is really a very simple method really, there's very little that's quantum about it. We're just treating the electrons in isolation. We're using the energy for a 1 electron atom, which we're applying to many electrons, just by looking at 1 electron at a time and pretending that all the other electrons are just sort of absorbed into the nuclear charge. And we still get some fairly decent answers out, good enough that it's kind of worth the effort to use Slater's rules in calculations. But we can get more accurate results, which we'll see later on.